We have an intuitive notion of what we mean by a limit, but that intuitive notion of a limit really isn't precise enough to verify some of the more dubious properties of limits. So really we need to come up with a precise definition of a limit. This is our intuitive idea for what a limit means, right? If the limit as x goes to a of f of x is L, sort of our idea for what that means is that as x gets closer and closer to a, f of x gets closer and closer to L. So, the classic picture here is if a is here, then L is going to be here, and as we start to either side of a and move towards a, the resulting outputs of the function, the resulting outputs of the function are going to look like this, and they move closer and closer to L like that. But, this this phrase closer and closer, it's hard to know exactly how to make that precise. It's sort of a very clear intuitive idea, but it's not exactly mathematically precise. And it's very hard to know how to proceed. But one thing you can try when this sort of thing happens, right here we're starting with describing what's happening in x and then turning that into a description of, or just turning that into a cause that happens in y, or in the outputs of the function. One thing you can do to sort of give yourself more ideas or more options to how to describe the situation is turn this around. Instead of starting with the inputs and then describing the outputs, we could start with the outputs and describe the inputs. So if you look at it that way, what's happening here is, we have some range of outputs, and there's a corresponding range of inputs that the function sort of fits inside of this range of outputs. You can see for any input in this range, the function sort of turns this into outputs that are inside this range of y values. So looking at it that way, we could describe a limit this way. So if we want to make the value of our function close enough to L, we just have to make x close enough to a. So if you sort of sketch a few examples of this on this graph, you'll see that this is really describing the same idea of a limit. So, the idea is no matter how close we want to get to the value of the limit, we should be able to find some range of x values that the function fits inside of that range of y values, right? And since these y values are clustering around this value L, this is what makes L the limit as x approaches a. All right, so this is a different way of saying it, but this really isn't any more precise because we're using this kind of vague phrase, close enough. So maybe what we should do is actually name how close we're getting to L. So the distance that we're going to let ourselves get from L, either above or below, we're going to call that distance epsilon. So this is a lowercase Greek e, epsilon. And the reason that we're going to use Greek letters is because everyone uses Greek letters in this context. So by close enough, what we're going to mean is within epsilon of L. So that's what's going to count as close enough. And then by close enough to a, well, we need to name how far we're getting from a here on either side. And we're going to call that distance delta. So this is a lowercase Greek d. And again, this is the traditional symbol for how far away from a you can get. So we'll use delta because everyone else does. So by close enough to a, we will mean within delta of a. So then what this phrase turns into is this phrase turns into if we want f of x to be epsilon close to L, that is within epsilon of L, we need x to be delta close, that is within delta close to A. Okay, so this is a little bit better, but what we really mean is, right, so we've drawn this picture for a certain value of epsilon, but really we want to be able to come up with a value of delta that works no matter how small epsilon is, right? The idea of a limit is that we can get arbitrarily close to the limit value. So really we want epsilon to be able to shrink down to 0. So we need to sort of add a clause before this definition. What we really need is for every positive value of epsilon, so for every epsilon greater than 0, if we want f of x to be epsilon close to L, then we need x to be delta close to A. All right. Well, so there's kind of a nice way to phrase being epsilon close to L and being delta close to A. So I'm going to actually write it for the delta version. So what we're really saying is that x has to be no more than delta away from A. But we can measure the distance between x and A by doing the absolute value of x minus A. So this is the distance between x and A. And to be delta close to A, we need x minus A to be less than delta. Okay. And so similarly, for f of x to be epsilon close to L, we'll want the distance between f of x and L, so which is the absolute value of f of x minus L, to be less than epsilon. Okay, so what we want is for every value of epsilon, we want there to be a delta, so that being delta close to A makes f of x epsilon close to L. So let's write that out. For every epsilon, so no matter how close we are to L, we want there to be a delta, which should also be positive. Both of these are positive. So no matter how close we get to L, there should be a delta that puts us close to A, so that if we are delta close to A, so that if absolute value of x minus A is less than delta, then f of x is delta close to L. So absolute value of f of x minus L is less than, I'm sorry, I said delta close, but it should be epsilon close to L. So this is our precise definition of a limit. You can see this, everything in here is perfectly well defined. There's no sort of intuitive notions left. So this is a precise definition of the limit. Okay, so we say that the limit of f of x as x approaches A is L when the following is true: for every real positive real epsilon, there's a real delta that's positive, so that when x is delta close to A, then f of x is delta epsilon close to L. So to see how this definition really encodes what we mean by a limit, let's look at an example. So suppose that our A value is here. You can see for this example, our L value is going to be right here. Okay, so epsilon is some radius around L. So here's a value for epsilon. What we need to do is, no matter how small epsilon gets, we need to choose a delta radius around A, so that this function sort of sends all our x values into this range of y values. Now, one funny thing about this definition is there just has to be some real number delta for this epsilon. It doesn't have to be anything in particular. We don't even need it to be as large as possible. We could choose a very small delta. So in our y values, we could make this be delta. So if we let ourselves go this far to either side of a, then does the function send all of these x values into the interval around L? Yes. Right? All of these x values, the function sends them into this this range around L that we're allowing ourselves because of this value of delta, or this value of epsilon. So for this epsilon, we found a delta that works. But remember, for a limit to exist, we have to find a delta for every positive epsilon. So we've done it for this epsilon. Now we have to shrink epsilon. So now let's make epsilon smaller. Like this. Well, now our old delta doesn't work anymore, and that's okay. We don't have to find a delta that works for every epsilon. We just need, for each epsilon, we can have a different delta. So for this epsilon, we're going to need a smaller delta, so maybe now delta is only this big, so much smaller than before. Now this function sends all of the x values in this interval into our new interval around L. So for this smaller epsilon, we found a new smaller delta that works. And for this particular example, I think you can see that if you shrunk epsilon even further, we could find a delta that works just by choosing one even smaller. And in fact, no matter how small epsilon gets for this example, we can find an even smaller delta that will work for it. So that's what happens when a limit exists. What does it look like when a limit doesn't exist? Well, here's an example of, clearly at x equals 3, there's no limit because the one-sided limits are different. But suppose you wanted to claim that you found a limit. So suppose you wanted to insist that this number, say 5.5, that L value works. So for every epsilon, is there a delta that works? Well, remember, epsilon can get really small, so what about this epsilon? Is there a delta that works for this epsilon? So we need to know around 3, that's our a value. Is there a delta small enough so that the function sends us into this range of y values? Well, what about this delta? Maybe this one is small enough. Well, if you look at what the function does to this red interval of x values, so that picks up this part of the graph up here, so these x values. And to the left of a, it picks up this part of the graph down here, and so that's these y values. Well, you can see we got some y values that don't fit into the interval around L. So this delta does not work. And making delta smaller isn't going to help because we're always going to pick up some of these y values down here, and those are never going to fit up into our interval around L. So that shows that this particular L value is not the limit as x goes to 3. Okay, well maybe the problem is we just picked the wrong L value. So let's change our value for L and see if we can find a limit. The problem with the first L value was that the value of the function is down here, so if we want a limit to exist, probably it should be down here. So let's try this value for L. Okay, now we can play the same game. For every epsilon, we need to find a delta. So here's an epsilon. Is there a delta that will work so that the interval around A gets sent into this interval around L? Well, what about this delta? Is this delta small enough? At first, things are looking good because to the left of A, all of these x values get sent into the interval around L, so that's looking good. But to the right of A, we again pick up this part of the graph way up here, and these this part of the graph gives us these y values up here, but these y values don't fit into the interval around L. So again, for this particular epsilon, there's no delta that will work, because no matter how small delta is, it's going to pick up some piece of the graph up here, and that won't fit into the interval around L. So this L value is also not the limit at 3. But, with these two examples of L values, I think you can convince yourself that no matter what L value you proposed as a value for the limit, if we just choose a very small epsilon, right, any delta is going to pick up part of the graph to the left and part of the graph to the right, and so we're going to get these widely separated y values. And so no matter what possible value for the limit you chose, these widely separated pieces are never going to fit into an interval around L as long as epsilon is small enough. So for this example, we see that the precise definition of a limit says that there is no value for a limit. And so that matches our intuition, right? So we have two examples, an example where a limit doesn't exist and an example where a limit does exist. And although it's a little clumsy, this epsilon delta definition for a limit does match our intuition. So this is the definition for a limit that is sort of mathematically precise enough to actually prove things with.